One more talk before lunch. Welcome Tobias Heister. He's talking, his talk is about control plane, data plane testing to convergence and beyond.
Yep. Yeah, thanks for having me. The test is, as I formerly mentioned, control plane, data plane testing. We have to define a couple of things before we can actually start with testing, but I would like to let you know how I ended up actually doing that and what led me there. Working for a company which all of you should have seen because they're there on your lanyards. Solution architect by day, worked with a couple of you guys over the years, building networks, trying to get it working, but I'm also one of the keepers of our lab facilities where we try to make testing as accessible as possible for internal and external people. I actually did a talk on how we do stuff in our lab, what we automate a couple of DENOGs ago, so if you're interested, it's on the slides. It desperately needs an update because we've done so much in between, but it is what it is. Conveniently, we also have a lot of technology in our labs, which comes handy on a later slide, hence I put it here as a teaser. As mentioned, if we want to talk about control plane, data plane convergence, by the way, this should have been an animation and a PowerPoint, so we now have a busy slide to start with because it's the PDF, but we work with that. First of all, the most interesting part, what's the control plane, what's the data plane? What we see in the top part of these slides, the slightly greenish, light greenish thing is our control plane. It's typically built on generic compute, some kind of CPU architecture, most commonly x86 these days, or maybe ARM MIPS, or have been PowerPC in the past. That's where your network operating system lives, that your vendor provides, that an open source network vendor provides, or whatever. This is where our routing protocol actually runs and does stuff. So we start on the top left side where our routing protocols live. They do some stuff, they do whatever they want to do, they receive updates, they do their computation, and they have some intermediate storage in there where they will put data into. Some vendors, and this is a common theme along the line, might already call that a RIP of some kind. So when I'm talking or using specific terms in my presentation, it's what I think it's a good idea to call them. Vendors might disagree, might call different things a RIP, a FIP, a forwarding table, but this is just what makes sense to me in order to explain it to all of you guys. So left side, let's stick to BGP, that's what most of the network operators are more used to. You consume updates, you put that into some database, and after that you have to actually export that into what's most commonly agreed to be the routing information base, the RIP. All of the protocols will dump their information, the best thing that the protocol selected, into the RIP, but the RIP will then contain stuff from multiple sources, multiple protocols, or multiple other things that actually wanted to put it into there. So what on a modern router that actually is a peering edge will happen is we will have millions of different prefixes or targets stored in that RIP, because if we receive prefix information from multiple BGP peers, they will first end up, all of them will end up in the same RIP, and they will just be candidates which can be selected upon. And we might have multiple different ways to actually get to a specific destination. So there might be different next hop, we might be using IP, we might be using MPLS, or whatever to get into these directions. So it's a very huge table which needs a lot of maintaining, and there's constantly churn somewhere, there's always back and forth in there. Most modern platforms will then already pre-compile something which is most commonly called a forwarding table. At this point, and from now on, we ignore all of the fancy features which will enable ECMP, which will enable failover scenarios like having a candidate route which can then be used. So we just focus on the old way of just having one destination. I'll come to that later. A typical forwarding table these days on a peering router has approximately 1 million targets which it needs to care about, plus minus 900K IPv4 targets, plus minus 150K IPv6 targets, a couple of internal routes which all have to be somehow known how and where to route. Typically, at this point in time, we only have one way and one destination for them. As mentioned, I exclude all of the fancy ECMP and whatever at that point in time. And now comes the fun part. Most modern router platforms have some form of data plane. Most expensive routers have the data plane actually implemented in hardware, and through the wonders of merchant silicon, even the data plane has become cheaper and cheaper over time. The data plane is typically no longer generalized compute. It's some special hardware, typically, I'll cover that in a minute, some form of forwarding chip. If it is a distributed system, a chassis-based system, there might actually be some helper CPUs on the individual line cards to actually help in consuming and building that stuff. So what happens, the forwarding table that we built on the control plane, we push that down into the data plane, which is then called forwarding information base. The only thing interesting which happens in there is that the generalized destination information that we had on our RIP, which might have been an IP address, might be more well, specialized now. For Ethernet, you no longer need the destination IP, you need the destination MAC address, which had to come somewhere. It was resolved and put in there. The last step in the chain is actually how to program the ASIC. ASIC, I use that term very loosely here. There's another workshop I did a couple years ago why ASICs are no longer ASICs, but it has to be programmed into the real hardware. And all of this stuff takes time. How much time does it take before it actually is, well, ready to be used in the data plane? There is a control plane data plane testing methodology. When I looked at it a couple of years ago, it wasn't that easy to find an openly available solution. So what I did back in the day, I used what we had in our lab, Keysight/Ixia tester, and that's what I'm talking about today, but I'll cover the other options we have in a bit. The test setup is a little bit like you see in the upper part of the slide. You have a device under test, that's the DOT in the middle. You have 3 ports. You have 1 transmitter port, where we just send a beacon prefix, which we will be using for sourcing of traffic, and we have 2 receive ports on the right side. On both of these receive ports, again, a completely oversimplified, deliberately very dumb example. I'm just announcing 900,000/24 IPv4 addresses. This has nothing to do with the real-world full table, which has different prefix sizes and all of that. But we want to make it as simple as possible to, well, keep it comparable what we do with the routers. So we have 2 of them. We announce the exact same prefixes via both of these paths. We prefer the way via RX1 by local perf. That's the only thing we actually do on a router. No other policies, nothing. So it should be as fast as possible, in theory. We then start our test traffic. We send traffic from TX to all of these 900,000 prefixes. One assumption is if a prefix is programmed, then it doesn't matter to which destination IP address in that prefix we hit. So we just hit send traffic to one IP of that /24, which ends up in 900,000 flows, which we need to look at. We then define a relevant rate for what we want to do. A relevant rate is, well, we need a resolution. So if we want to hit each prefix once per second, we need to have 900,000 PPS. If we want to have a lower or higher resolution, we need to increase or decrease that. What we are actually measuring is then, we are simulating a control plane event. In this specific scenario, we're just withdrawing all of the 900,000 routes we had on RX1, and the network should converge and fail over to RX2. So the first thing we have is a control plane event. It takes a couple of seconds to crunch on the control plane. Then we will see something happening on the data plane. Route traffic will suddenly start to switch over to RX2. But some traffic will still continue to be on RX1 because not all prefixes will be programmed and available at the same time. And after some time, the data plane will have converged. Traffic will be completely on RX2. And these are the 3 events we have: control plane event to withdrawal, the first sign of traffic being moved, and then the second sign, all traffic is being moved. And then we can actually look at 2 convergence times. The first one is the data plane to data plane, so first data plane event to last, when was the traffic shifting. And the control plane to data plane convergence, so when did we start the actual external event, and when did we see a full effect of all of that, which we can make use to look into a couple of numbers. The interesting thing, I think, is the end-to-end convergence time. And as I mentioned earlier, we have quite a big lab. We actually have the biggest Juniper lab outside of the vendor in Europe. So I have pretty much all of the Juniper devices that can hold a full table there. So when you're bored, what do? You just test all of them. And see how they compare to have a baseline. And that's what the next slide shows. There's once again a blog post we had at Zantaro that we published. I categorized them a bit in a couple of categories. I've said everything below 30 seconds is good, everything below 90 seconds is okay-ish. And then we obviously have to have our most to be picked upon routers from Juniper MX80 and 104, who everybody hates for being notoriously slow. A couple of things to note. There are a couple of software-based platforms in here, SRX series. They're not meant to take a full table, but I know some of you guys are abusing them to do so, and they are fine in actually doing it. Just be aware, they converge very, very slow if you actually do so. And this is one of the most simple ways of doing it, so if you get more complex, it will even get worse. So now what do we do with that? I know that I'm running out of time, but I have a small call to action. I think and I defined it we along the way, what we should do with that information, we, the DENOG community, that's basically all of you, using our routing working group. First meeting is basically after lunch. Vincent's instantiated that. It started last year, but it's now instantiated. We should define a standard set of BGP policies which we can actually torture the devices with. So not only have no policies, but have a reasonable amount of policies to make it even slower. We, as the DENOG community, should find a way to have an open test suite, which is not Ixia-based. One thing we could use is Christian's BNG blaster we saw earlier. We actually talked about the conference, and we think we can make that working pretty quick. If we can't make that working pretty quick, we, Zantaro, we can offer to actually run these things for free for you in our lab facilities in Frankfurt. We have the Ixia there. The offer, there's a couple of terms and conditions in there. It's only for this data plane test, because otherwise I would not have been allowed to offer this for free. Come, bring your router, we test it for you. The only demand we have, we need to publish that stuff publicly afterwards. Which brings me to the last point, where should we publish that stuff? It doesn't work if we put it all into our individual blobs. Let's find a way, community, DENOG website, wiki, wherever, where we can publish that stuff, make it available to the community. Last thing, kind of a bit of a teaser, when we actually want to do the testing, there will be a DENOG meetup hosted at the Zantaro facilities in February. If you happen to have a router in your luggage when you're coming over, that would be a convenient time to just do some testing with us if you want to come a bit earlier or leave later. So if you want to torture routers, bring them with you. We find a way. Sorry.
Tobias, thank you.